The following presentation is part of the Technology and the Corporation Conference Series, sponsored by MIT's Industrial Liaison Program.
Thanks very much, and thank you all for being here, and thank you for inviting me to be here this morning. I came at manufacturing through my entrepreneurship. I have been an academic most of my life until very recently, but along the way I was always starting companies and trying to build stuff. And I found myself chasing low-cost manufacturing through southern China into Vietnam, which made me start thinking about the future of manufacturing. And this is a question for me, you know, I mistyped that. Will our consumer goods always be manufactured by hand? I was doing this late last night. And for this audience, you know what it's like in a Chinese factory in Shenzhen. There's lots of people sitting there. There are lots of people doing stuff by hand. These people are by hand building robots, which is interesting. But a lot of hand operations. We've had a lot in the news recently about Foxconn and Apple, and there was a story, ABC Nightline, where Apple was getting beaten up a little bit for their manufacturing practices, but we could beat up many companies in exactly the same way, whether they deserve to be beat up or not. But one of the interesting things was an iPad is touched by, in this report at least, is touched by 325 pairs of hands during assembly. So we build our stuff. We build our stuff by hand. Now, building by hand, not as artisans, but by turning people into robots doing the same thing one step at a time. And why one step at a time? So they don't get cognitively overloaded and forget a step, because there's just one thing they're doing. And that's how you break out the assembly operations in China. Now, will we, is it possible 200 years from now that we'll still be building the stuff we use in everyday life by hand? Does anyone think 200 years from now we'll still be doing that? You do? Someone thinks in 200 years we'll build... Ooh, that's a long time to be building stuff by hand. Here's something else that we used to do by hand. We used to send commercial telegrams by hand. People would get a message, they would read it, and then by hand, using their hands, they'd tap it into the electrical system, and at the other end, someone would be listening and by hand write it out or type it in and get it sent off. And commercial telegrams were sent by hand for a long time. The first ones in the US were sent in January 1838. When do you think the last commercial telegram was sent by hand in the US? Sorry? 1973, no, 2006. The last week of January, there were 10 telegrams, or 20 telegrams sent by Western Union. They gave up at that point. They said, not enough. But so maybe you're right. Maybe 200 years from now, we'll still be manufacturing all our stuff by hand. But I hope not. Those jobs are terrible jobs, manufacturing by hand. We've been making stuff by hand in factories pretty much for 232 years, roughly. And as we know, manufacturing is still strong in the US. Productivity in the manufacturing sector has increased faster than other productivity. And manufacturing output has increased by 3.7% per year for 60 years with mostly flat employment. Now, how has that happened? It's happened by moving stuff offshore where there is low productivity. And so we've gone to more and more higher value-add stuff in our mix in the US and let the low value-add stuff go offshore. So since World War II, our by-hand manufacturing shifted to Japan, and as their economy went up, it shifted to South Korea, and as their economy went up, it shifted to Taiwan, and then it moved into southern China, then it moved down to Vietnam. In the 90s already it was moving to Vietnam. There's more and more, these are long-term processes. But at the same time, the other countries down there, Thailand, Malaysia, to a lesser extent Indonesia, have had their own increase in standard of living. And so we're running out of places for this flow of low-cost, by-hand manufacturing to go, which is why I don't think it's going to work for 200 years, by the way. And if you look at the labor costs in countries, you see exactly this geographic route in the costs in the different countries, and they follow up. And so Germany and France have higher labor costs than the US, but then you see the trajectory of where these labor costs went. And you've seen what's happened in the last 2 years with Foxconn and their wage increases. So what will it take to break out of making cheap stuff by hand? How do I prove my friend up there wrong, that it's not going to be 200 years that we're still going to be doing this by hand? And advanced manufacturing, I think, is the answer, but I think in the US we've sometimes got confused about what advanced manufacturing could be. We've sometimes confused advanced manufacturing with manufacturing advanced stuff, which is important, and that's how the US has increased its productivity, by only keeping manufacturing the advanced stuff. But I'm not sure that's sustainable. I was on a panel at the National Academy of Engineering in October, and I was sitting next to Craig Barrett, former chairman of Intel, and he was saying on the panel, we have to find the stuff that we can make in the US that no one else can make, and that's what we should concentrate on. Well, that's an ever decreasing, narrow sort of thing that we can go after. I'm interested in advanced manufacturing for manufacturing the ordinary stuff, the stuff that we currently manufacture by hand. That's where I'd like to get to. It's very rare that I've been speaking and I already have -5 minutes. I'm confused by this. We started early. So as we think about that higher volume going down to the necessities, how do we deal with that? How do we manufacture that in the US, given the theme? And why manufacture in the US? And John Reed mentioned a few things. I want to go through them in a little more. This is, from my point of view, as having been a manufacturer at iRobot of consumer goods that was sold through retail. This is where I've seen some of the pain points. First, responsive short supply chains. If you're putting stuff into retail these days, every retail outlet wants their own pack out. Costco wants a different pack out than Sears. Sears wants a different pack out than Target, etc. So you're trying to predict market needs 6 months, 30 weeks ahead of time, but not just how much stuff you're going to sell in the US, but how much stuff you're going to sell in each channel. And who knows whether some of those channels are going to be around in 30 weeks. So you're trying to say, how much stuff do I need here? How much stuff do I need there? Different pack out. So that makes predicting and managing tightly very difficult, and getting shorter supply chains is helpful. Some people are doing that by building modules in China and then doing pack out in Mexico and then shipping across the border, so that those final decisions can wait later. John mentioned innovation close to manufacturing. I think this was underrated for many years, and by not having innovation and engineering close to manufacturing, we lost a lot of our innovation because it followed and got close to the manufacturing where it was. So bringing that back, bringing the manufacturing back, makes the innovation a lot better and makes it much more responsive to market needs. Protection of intellectual property is a big one. Every company that I talk to that's built consumer goods in China has said they have seen exact duplicates of their stuff out there for sale. I've had that happen at iRobot, certainly. We can't always tell whether they're using the same tools in the same factory that we're using as a contract manufacturer, or whether the tools have been copied. We don't know. It's very opaque, even though we have people on the ground in the factories, and this is a common story. So protection of intellectual property is a real issue here. If we can get our productivity up, it beats the cheap labor, because the cheap labor isn't the whole story, but we do need to increase our productivity. And lastly, higher transportation costs. In that storm of 2008, with the oil price spiking and the economy collapsing, a lot of people who are building retail stuff completely lost their margins just on oil surcharges, shipping stuff across the Pacific. I predict, and like my friend up there, about 200 years, I predict the cost of oil is going to increase over time. So that's going to be an issue. You heard it here first. I see an analogy here, and this is what's been driving me, that, and most of you are too young to remember this, but I do remember this. This is what computers used to be like. They were these big, ugly things with whole teams of people operating them. You had to be specialists to use them in any shape or form. Ordinary people couldn't touch computers. By the way, ordinary people couldn't touch. One of the reasons to keep out ordinary people was they all smoked, and the smoke particles got into the disk drives and crashed the disk. So ordinary people were dangerous to computers, it turned out. But then, around 1980, with the PC, we let ordinary people touch computers. And when they could touch computers, there was a whole series of innovations, a whole series of changes of forms, things that were unbelievable and magical in the old days when you used punch cards to program computers, completely changed what computation was and how people used computation. And by the way, when that happened, people said, oh my God, we're going to lose all the jobs in offices. I think there are still people working in offices, a lot of them. It didn't get rid of office jobs. So letting people have computers didn't get rid of office jobs. It changed the work they did. And now robots, I've been a roboticist most of my life. Robots are like those old mainframes today. Ordinary people can't touch them. One of the reasons ordinary people can't touch them is the robots are dangerous to the people. It's flipped around in this case, because the robots aren't aware of people and they'll just knock their heads off. But what if ordinary people could touch robots? And there has been a transformation in this over the last 10 years. Ordinary people can touch robots, but not in the manufacturing domain at the moment, in the other domains. So intuitive surgical up there on the left, whether you count a surgeon as an ordinary person or not, and they'll give you an answer for a different reason that you might, they're touching the robots and operating with robots. But then there's the home robots, the fulfillment centers over on the right, Kiva Systems, just sold here in Massachusetts a few weeks ago. And then a big change in our military robots. And I'm going to come back to those in a few minutes. But an important point about the military robots. Who are the users of the military robots? They're 19-year-old kids. 19-year-old kids who used to be put in bomb suits to go out and poke bombs with a stick with a rope tied around them to pull them back. It's ordinary kids, 19 years old, who are out using those robots. There's been an uptake over the last 10 years in unstructured environments, environments where where the world is not built for the robots, but the robots are going into an ordinary world. June 2002, there were 0 robots, ground robots in the US military. There's about 12,000 of them now. First 2 were sent by MIT spin-off, my company, iRobot. First 2 were sent to Bagram Air Force Base in June of 2002. And up from there, an uptake of 12,000 by a bunch of manufacturers. And then robots in people's homes. There were 0 robots in people's homes in June of 2002. Just iRobot alone has now shipped over 7.5 million robots into people's homes. These are unstructured environments. The homes are not built for the robots are going into the existing environment. Very different from the way industrial robots have operated. So at iRobot, lots of robots in the homes doing different sorts of tasks, and lots of robots in the military, underwater, land, etc., doing different tasks, all operated by essentially untrained personnel. And why have things taken off in this last 10 years? Three reasons, I think. And then I'm going to talk about how this can come to manufacturing. Computation and sensors have gotten exponentially cheaper for the last 50 years. And I'm going to talk about exponentials in a minute. Something getting exponentially better is overused all the time. I see in news stories, it's exponentially, the Party A is doing exponentially better than Party B. Well, they can't be doing exponentially better than the other party. It doesn't make sense. So it's overused, but I'll come back to that and talk about that. Research in computer vision and simultaneous localization and mapping. Simultaneous localization and mapping means the robot is moving around and it's mapping out the objects and figuring out what's around it, at the same time figuring out what it's doing. Simultaneous localization and mapping has made tremendous strides over the last 15 years. A lot of it done here at MIT. And this is perhaps the most important. For certain tasks, robots have passed a usability threshold that makes them useful to untrained people. And I think that's the key. Making stuff easier to use is going to be the key here. I want to take a side walk here and talk about IT exponentials for a second, information technology exponentials, because that relates to what we can put in our factories. This is a 10-page magazine article, no, 5-page magazine article, sorry, written by Gordon Moore. Gordon Moore, we've all heard of Moore's Law. This is where Moore's Law came from, this 10-page article in 1965 in Electronics magazine. And he says, with unit cost falling as the number of components per circuit rises, by 1975, this is 1965, economics may, he was hedging, may dictate squeezing as many as 65,000 components on a single chip, 2 to the 16th. This is a fantastic little paper, this 5-page paper. I reread it every so often. It was brilliant. Here's what he says in the second paragraph. Integrated circuits will lead to such wonders as home computers. This was 1965, he was saying this. Automatic controls for automobiles. I've owned automobiles made in 1965 and before. There were not much in the way of electronics back in 1965 in automobiles. And this is the best one. Personal portable communications equipment. It's the cell phone. He predicted the cell phone at the time. And by the way, there was this cartoon in the paper. And I asked Gordon whether he'd had anything to do with the cartoon a few years ago. And he said, no, I opened up the magazine. There the cartoon was. But here's the cartoon. There's someone selling handy home computers right next to cosmetics. My guess is the cartoonist was sort of making fun of Gordon Moore and his predictions. Oh, yeah, we're going to have home computers, sure, 1965. But the laugh is on the cartoonist because this is exactly what has happened. OK, so this is the graph. And this is another lesson. You can't get away with 4 data points anymore in a scientific paper. He had a null data point down here, and he had 4 data points, 4. And this was how many components on a chip. And this is a log linear, that linear time, logarithm 2 to the power of number of components on a chip. And he just extrapolated. He only dared extrapolate 10 years out to 1975. And that's how he got 2 to the 16th components, maybe by 1975. Exponential growth. What is exponential growth? Well, exponential growth is that when the rate of change of the amount of stuff you have is proportional to the current amount of stuff you have. That's what makes an exponential. And is this how computer power, and chips have become exponential? Does the presence of computers of power P make it easier to build a computer of power WP, where W is greater than 1? Well, it does, but that wasn't in play in 1965. In 1965, this was integrated circuits. There were no computers with integrated circuits in them. The first computer with an integrated circuit was built just down the road in Draper Lab as the guidance computer for the Lunar Lander module. First Block 1 version operated in 1968. It had 1 gate per chip. Then, and things moved fast then, really. On the flight computer for the Apollo 11 lander, 1969, they had changed all the chips out, and they had 2 gates per chip. But so, powerful computers, oh, this is not a powerful computer. Powerful computers were not around and didn't make weren't the basis for the stuff in the same way, say, if you got a certain number of Facebook users, you get proportionally more Facebook users, which is why you get exponentials. But I think there's really 3 forms of exponentials. There's the rate of improvement is proportional to the current level of adoption. And that eventually happened with CAD and computers, et cetera, and made them chips better and better. But the existence of the law tells everyone what level to aim for. It was also very important for information technology. In Silicon Valley, every engineer who walked in every morning saw how many RAM bits they needed to get on a single chip in what year. It was just sitting there on a chart, and you knew what you had to aim for. But this is the important one for manufacturing and for robotics. Someone else is, I'm going to get a new one. Someone else is driving an exponential, and you get to hop on it for free. So other exponentials happen and get technology better and better and better, and you get to use it. And that's where manufacturing can really take advantage of IT exponentials. Unless we have robots building robots, we're not going to have sort of self-induced exponentials much. It's going to be other exponentials and using them. I'm going to give some examples of this in a second. But I also want to say why exponentials can only happen organically in information technology and not in other things. So information technology has a special relationship to physics, and I think people forget this, and I'll tell you where I think people have forgotten this in a minute. All digital abstractions, and I'm going to come back to manufacturing. This is a side thing. I'll get back to it. All digital instantiations of information technology are based on a one-bit abstraction for a bulk physical property. You know, there's a charge in the cell, there's no charge. There's a voltage, there's no voltage. It's a one-bit abstraction, yes, no. So, for instance, a pile of blue versus green sand. I've got these two piles here. That's a pile of blue sand on the left, a pile of green sand on the right. I can take away half that stuff. I've still got a pile of blue sand versus a pile of green sand. I can do it again. I can do it again. I can keep doing it. I can keep taking away half of it again and again. You know, eventually I get down to, oops. Oh, where are we? Eventually, if I get down to a single grain, it doesn't work anymore, and that's why we need multi-core chips for those of you in that business. But we can keep cutting stuff in half, and the one-bit abstraction still holds. That holds in this information technology realm. It doesn't hold in other realms. But it means there's lots of technology exponentials to be had all over the place. But in other domains, physical bulk matters. So a big industrial robot, if you cut away half of it, it's not going to retain its strength. And if you cut away half of it twice or three times, it's going to fall down. So you can't just get organic exponentials in everything, only in information technology. And by the way, I think that's what led venture capitalists astray in clean tech. They were used to, in Silicon Valley, having every business go exponential. Then they started doing it with bulk stuff in energy, and it didn't go exponential organically because it wasn't about an abstraction. It was about real stuff. So we have to be careful about that. But nevertheless, with these IT exponentials, do help manufacturing, they do help robotics because other people have exponentials and you get to hop on it for free. So exponentials impact robots. This is the very first robot I worked on professionally. This robot over here, you can just see it there with wheels, and it would roll around to here. And on there is this camera, and the camera physically slides side to side. And it slides side to side because the camera was $50,000. This was in 1979. We couldn't afford two of them. So we wanted to get stereo vision, so we had to slide the camera mechanically side to side. And this was Hans Marovec's project, and I was his junior gopher as a grad student. And after everyone else went home at night, around midnight, we'd set up the robot. From midnight to 6 a.m., if we were lucky, it would go 20 meters across here. It would take two images, compute for 15 minutes on the mainframe, and then move a meter. So 20 meters in 6 hours was what a robot could do in 1979. And it had this $50,000 camera on it. About 2 years ago, I saw a webcam for sale for $2.99. I bought 5 of them. They were horrible web cameras, but they were so much better than this $50,000 camera that we had to struggle with in 1979. There's an exponential that has improved what we can do with automation and other systems, because cameras have gotten, really, they did get exponentially cheaper for a long time because they were driven by consumer need or consumer want for digital photography and for home videos. I don't know what's going on here. Oops. So that was in 1979, 20 meters in 6 hours. This was one of my robots here at MIT in 1992. This was a robot Polly, which would give tours of the artificial intelligence lab when you came up to it. It would talk to you and drive itself around with a camera on board. It would go 2,000 meters in 6 hours. And then in 2005, Sebastian Thrun from the same lab, Stanford Artificial Intelligence Lab, won the DARPA Grand Challenge and went 200 kilometers in 6 hours with a robot system. And so that was 13 doublings in 26 years. The capacity of the robot doubled every 2 years, largely due to technology driven, the exponentials of other technologies. The amount of computation one could put on board. This had to be off board with a slow transmission link. Transmission links got faster and faster because of modems. This one had its processing on board with a TI DSP, and this one had all its processing on board with Intel array processors on there. So I think the world needs robots in order to help with manufacturing and help productivity. But unfortunately, our industrial robots got stuck badly somewhere along the way. The world's first industrial robot was built by Joe Engelberger, who's still alive, and it was the Unimate, a company called Unimation, Universal Automation. First installed in a GM factory in 1961 in New Jersey. That was the first industrial robot. Later, by the way, Unimation was bought by Westinghouse, and then it was sold to Kawasaki. Now, there were a lot of technology limitations back in 1961. You couldn't have a computer or sensors. They were too expensive. There weren't even mini computers back then. You couldn't just have a computer attached to the robot. So these robots had no computers attached to them. They virtually had no sensors. They used PLCs, one-bit operations. But what they were good at was doing the same motion repetitively. And that was the solution that industrial robots gave you. They did the same thing again and again and again. And unfortunately, that is what industrial robots have competed on for the last 51 years, doing the same thing with precision and repeatability. These robots are unsafe for people to be around because they come just as a robot with no external sensors. You have to have systems integrators to add on the external stuff, and so it's external sensors. So essentially you have a cage around the robot, and if you step into it, then the robot shuts down. So if you go to an automotive factory, you'll see lots of robots in the body shop where the bodies are built, and no people. There's a boundary. People don't go inside that boundary. The robots operate, and because there are no people in there, the robots better operate with 100% reliability. Otherwise, you have to shut the thing down so people can go in and fix stuff. That's bad. But what's happened is industrial robots have engineered to be precise and repeatable, and we haven't worried about them being adaptable, flexible, or easy to use. What do I mean by these things? Adaptable. Adaptable means if you move stuff in the environment a little bit, the robot doesn't know where it is because it's not really sensing. It's just repeating a motion and going there to grab. You have a worker in a Foxconn factory and something comes down on the conveyor, offset a little bit, the person sees it and adapts and goes to get it. The robots are not flexible. That was the promise of robots. We'd be able to reprogram them easily, but the programming systems are so arcane, it takes specialists and months to program them to do new tasks. I'm not going to name names, but there was one of the manufacturers of industrial robots has an easy-to-use programming system, and it comes with a manual 322 pages thick. And it says on the first page, it is assumed you have read these other things, and those other things are this thick. And that's for starters before you get into it. It's only easy to use for an MIT engineer, and I'm going to come back to that. There is a certain sort of macho-ness about robots. They're complicated. They're hard to use. I was with the chief of technology of a European robot company just in November, and I was talking about having line workers reprogram robots, and he bristled at that. But robots are complicated, and he was proud of the complications of robots, and letting ordinary people touch them wasn't such a good idea. And so that's that ease of use, which has not been competed on. So these robots are not adaptable, so they have to operate in very structured environments. Their application is limited as a result, and the integration cost is 5 to 10 times the capital cost of the robots. The cost of the robots isn't the most expensive thing about putting a robot anywhere. So robots don't exist in small and medium enterprises. So here's a current industrial robot with its 900-pound robot controller, but they ain't like this. We have done something different with our consumer electronics and with our computers for offices, and we've made them easy to use in a way that no one has been worried about for automation. And that's generally true of our automation equipment. Our automation equipment is the place where the professionals go to operate it, and high-paid consultants. It's not where ordinary people get to operate the stuff. Now, I'm going to give you some examples of just a few here. And I'm embarrassed that, I started early. I'm going to finish early. I'm sorry about this. I'm not used to this. In my lab at MIT, we built robots with human form that could interact with people. I'm just going to show a couple of examples here, although, this video does work. Here the robot sees her. She gets its attention. She looks at an object, and the robot sees what she's looking at and looks at the same thing and then goes off to reach out for it. Very different from what an industrial robot is. It's adapting to it. Here is a... oh, golly. That's what I get for putting this talk together at midnight last night. This movie is not linked for some reason either. Okay. What was going to happen there was this person is going to move this object around. The robot's going to see it. He puts it down on the table, and then the robot pushes it to segment it, and then it can see what the object is. Hopefully this one's going to work. Okay, that's not working. So I'm just going to give up here, and I'm going to go find this movie because I'm going to show you one of them. Okay, at least you'll see one movie here. So here's a robot that's interacting with a person up close. This is not like an industrial robot at all. If you get close to an industrial robot like that, you will not like it. It will not be pleasant. Here, the robot and the person are interacting. This was NASA-funded work. This was meant to be a robot that was going to help out astronauts. It's tracking him. It's adapting to him. The robot, and the person are going back and forth. Here's a very unstructured environment. The robot's holding a hammer. It's never seen this hammer before. There's a cluttered background. It moves it around. It feels the force as it moves it around. It starts to predict, as you would if you picked up a tool. You'd feel how it felt. You'd be able to move it. You'd be able to predict. Be very adaptable in a cluttered situation. Here, the robot's task is to put a pipe in a hole. It's never seen this pipe before. It's never seen this hole before. It moves them around, sees how they move against the background, estimates their size, their distance. That's that wiggling that's going on there. And then this is Aaron Edsinger, the grad student who did this. Then it goes in and inserts the object in the hole, never having seen either of those before. Okay, I'm gonna quit that. By the way, at Aaron's thesis defense, he had the robot make a margarita. Not a really good margarita. But here's the important thing, I think, for people thinking about tools to make American workers more productive, is you have to adapt to your end users. And that is what the robotics industry has not done. It has not adapted to the end users. It's adapted to the specialists. The people who make the robots have been marketing to specialists, have been marketing to the systems integrators, who have a vested interest in having the stuff complex to use because then they're needed by the end users. But it decreases the market overall. So here's an example of this. These are iRobot packbots used in Afghanistan and Iraq. This is a little interesting story. This is the head of one of these robots, the back of the head, Scooby-Doo. These robots are sent out. They go and push around IEDs. Sometimes the IEDs blow up, but instead of the operator getting blown up, sometimes the robot gets blown up. So this guy came in, or this isn't actually the guy, this is someone in a depot. A guy brought in this robot that had got blown up, Scooby-Doo, into the depot and said, can you fix it? And no, but we'll give you a replacement. No, 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 this is Scooby-Doo. We've been through a lot together. And this is the back of Scooby-Doo's head here. And you see one vehicle-based improvised device, 17 improvised explosive device, and 1 unexploded ordnance. So it had 19 successful missions before it blew up, saving the life of the operator. The operator really felt close to it. Different sort of thing than we had thought about with robots. But what happened was when we built these robots at iRobot, we had a lot of MIT engineers. And one of them, who will remain nameless, Pavlo Rudachevek, was very proud of the interface we had on essentially a hardened laptop with all sorts of menus, and there were some joysticks there, force-reflecting joysticks, and you could do anything with this robot. You could get at everything with this menu system. And from the field, from Iraq, came back word that iRobot's interface, to use a technical term, sucked. This was astonishing to our MIT engineers. Pavlo said, well, we need smarter users then. That was not the right response. Instead, you need to adapt to the users. And automation equipment has not been adapting to end users, to the people in the factory. The people in the factory have been considered different. They're not the people who, it's the engineers who know how to use the stuff. It's not the people in the factory who know how to use the stuff. So what did we do? We did a hardened, essentially Game Boy controller, attached that to the robot, shipped those. Now, could we do 100% of what an engineer could do with that user interface with the robot? No, couldn't do 100%. But with 0 training, 5 minutes of playing, 85% of the capability was available to the average user in the field. The average user never got to 85% of the capability with the menu system and all the setting parameters and stuff. So we gave up 100% usability, or 100% capability of the robot for having a better user interface, and it became more useful to people in the field. Same thing happened, by the way, with the iPhone. When the iPhone came out, well, first of all, an iPhone, it's a computer, but you can't write code for it on the iPhone. That was given up. You don't program the iPhone on the iPhone. It's programmed somewhere else. You don't have that capability. But even ordinary users of the iPhone were first really annoyed. It doesn't have cut and paste. How can this be a real device if it doesn't have cut and paste? Well, we managed to use it for a few years with no cut and paste. We gave up that capability for ease of use. It was only after working for a while that we got cut and paste on the iPhone, and I think most people don't use it much at all anyway. It's not necessary. So giving up capability for ease of use goes against everything engineers think about, goes against what manufacturing engineers think about, but it is what has made consumer electronics so successful, giving up capability for ease of use. It's a different mindset. Now, manufacturing innovations in this space are starting to bubble. Lots and lots of little companies. I'm just going to talk about a few of them. I'm going to say a little bit about my company, Heartland Robotics. We're trying to make robots that are easy for ordinary people to use, easy to buy, train, and deploy, and unbelievably inexpensive. And we're making them in the US, by the way. These are complex products, but with lots of ordinary stuff in them, lots of gearboxes. And we've set up a supply chain in the US, which I think will surprise people because of the complexity of the device we're building and the cost that we're building it at. But it has taken a lot of work to do that. But what we're trying to do is put robots that ordinary factory workers can interact with and program rather than specialized people programming. We haven't shown the product yet. I think the Boston Globe broke the story yesterday that we will be showing the product. You will see the product this calendar year, so we will be coming out. Sorry, I can't talk more about that right now. But here's another company, MFG.com. Anyone here worked with MFG.com? Anyone heard of MFG.com? Few people have heard of it. Okay, so I love MFG.com. I've been using it for quite a while. Here's it's a web-based marketplace for small lot manufacturing. You place an RFP on the site. Small companies reply with bids. You use web-based payment, FedEx delivery, and there's reputation building on it. This is a snapshot I took on, and I think my battery's running out now, a snapshot from the website on Sunday night. There was $158 million worth of contracts for fabrication open. There was $17 or $18 million of casting open, etc. So it's a real business. Real people are using it to do stuff. Here's a snapshot. This one was taken in I think in January. This was some recent things that had just happened, and you see all sorts of stuff. You see, what have we got here? An automotive buyer in Colorado is using a machine shop in Nashua, New Hampshire. A consumer products buyer in Livermore, California is using a machine shop in Melbourne, Florida. It goes on like this. Different parts of the country using machine shops and small operations across the country. This works because there have been some enablers. Universal availability of the internet, web standards and browsers, so all the customers and the suppliers go on and use their web browsers. High-end 3D CAD for machined parts mostly. We don't have good CAD, as good a CAD as we need necessarily for cast products. But for machine stuff, that's pretty well under control. And spreadsheets for personal computers. Web-based payment services, and overnight shipping services. When you put all these together and then have a new business model around it, what's happened is tiny, one-person and up, two-person companies that used to have an addressable market of maybe 3 miles now have a national addressable market. So these technologies, when applied to small lot manufacturing, have changed the business model for lots and lots of small companies. So I think this is important. This is an important example of how technologies, these technologies were not developed for small lot manufacturing. These were developed for other stuff. Then MFG.com came and put them together and changed who supplied who, and you can get small run prototyping and manufacture turned around in 48 hours from your, and if you're doing prototypes, this is the way to build stuff early on. It's not the way to do large-scale manufacturing, although some people are using it to do their whole business model. I have an MIT graduate 24-year-old daughter who has a Silicon Valley company who's building all her stuff this way. So some people do it. Here's another thing, MakerBot 3D printer. There are lots of 3D printer companies, cheap printer companies. Look how cheap this damn thing is. It's made from laser cut wood. Laser cutter, another technology that was developed for us. Laser cut wood, and the electronics for this are the Arduino system. Arduino is this easy to use hobbyist programming system that came out of an earlier project actually here at the Media Lab in making graphics easy to program. And now there's lots and lots of suppliers of that electronics. Put this together and make a $1,300 3D printer. Is it as good as the high-end ones? No. But again, some companies are using this to build their actual product. They're certainly using it for early prototypes. Can this be serious? Really? A wooden 3D printer? It can't be serious. This can't have any impact on the world, can it? That was the Apple I. No impact, ever. So, Monday's Economy. Economy is a local technology website spun out of MIT. Ford offering employees free tech shop memberships to spur innovation. Tech shops are these places where they have lots of equipment. You go in and you get to use it as a hobbyist. Again, a lot of little companies are using tech shops and the other competing places as their place to do rapid prototyping. And Ford is now getting to that. So there's a bubbling here of different models going on, starting to happen. We're starting to see some new categories of industrial robots. The one on the left is from a company called Kawada Industries. Kawada Industries makes steel for bridges in Japan. The grandson of the founder had to do a side business. He started building helicopters in Japan, and then the Japanese economy tanked. So he went to robots and is trying to build a new class of industrial robot at Kawada Industries. This is a conceptual prototype from the European Union SME Robot Initiative, Small Medium Enterprise Robot Initiative, which was a highly funded project under one of their frameworks there to the traditional robot companies about having a robot that you could interact with safely. They didn't quite get there, but at least people are thinking about it. So there's new categories coming around people are starting to think about. This now starts to get tricky. When you have new categories, you need new standards. This is an example I like. This is the 1865 Red Flag Act in Britain. Put a 4-mile-per-hour limit on street locomotives and required a 3-man crew. Why did it require a 3-man crew? Well, it needed someone to walk in front with a red flag. It needed a stoker because they were coal-powered. They were steam locomotives, not on rails, and it needed a driver. So the Act came in and said you need 3 people to drive a car in Britain in 1865. Then the train lobby got a hold of this. And as technology increased, the train lobby resisted and resisted and resisted any change in this regulations for cars because it made cars impractical. So it wasn't until 1896 with the Locomotives on the Highway Act that they eliminated the red flag. They eliminated the 3-man crew because by now they had gasoline engines, and they upped the speed limit to 14 miles per hour. And people may have heard the London-Brighton vintage car run that happens every year. That's in celebration of this 1896 Act. So what in 1865 was a sensible set of regulations was no longer sensible 31 years later, but entrenched interests really fought the change in regulations, the safety regulations. We see that happening now in industrial automation equipment. Sensible regulations that were there are fought by the safety equipment providers because that's going to get rid of their business if you don't need the safety equipment anymore. But the change of category from locomotive to automobiles eventually required a change in regulations. At iRobot, we've sold they have sold, I'm not associated with them anymore, 7.5 million Roombas. Fortunately, there were no applicable mobility standards when we started selling them. Because if they had, we wouldn't have gotten those robots out for sale. They would have been, if they had come under the automated guided vehicle standard, which fortunately they didn't quite, then they would have had to have a meter-high stick with a flashing yellow light on them, which would not have helped them go into beds and clean under there. So we had them on the market before anyone thought to invent the regulations for them, which was fortunate. Now, we had safety in mind. We've got triply redundant systems on them so to stop them falling downstairs. We've never had a single safety claim has been filed on 7.5 million. So sometimes innovators can do it right. And now I'm old enough. When I was a kid, computers had emergency stops on them. There were these big red buttons, and I don't know what the emergency was exactly, but the big red button was bigger than the iPhone. This is my first computer. It had that big red button there. And you had to get a customer engineer out from IBM to fix it if you pulled that, worried about what the computer was going to do. New categories do involve new vulnerabilities. This is an Athon hospital tug. Now it's networked. It's networked so the network control center can get out of trouble when it's in trouble. But maybe we're going to have hackers come into our robots. So there are new vulnerabilities. There do need to be standards, but they're different standards from what we had before. And new categories meet changing needs in industrial automation, industrial robots. All these things that are just common today are going to go away. They're not going to be needed anymore. And as we have new categories, there's going to be new business models. And I think that with automation equipment that ordinary people can use, like MFG.com, where small, not highly educated people, not people with MIT engineering degrees, but small outfits are going to be able to get into the business of doing manufacturing in ways we don't think of right now. So when Walmart right now wants a new, or wants to sell some particular item, they will have them manufactured in China, but maybe in the future, instead, they put up and say, I need 10,000 of these in my Kansas warehouse. I need 15,000 of them in my Seattle warehouse. I need this and that. You figure out how to do it. Here's the spec for the product. And it's done by a whole set of different companies, different sorts of companies than the contract manufacturers we currently have in China. I think there's lots and lots of possibilities for complete changes in business models over the next few years as people concentrate on making automation equipment and productivity equipment that ordinary people can use. That's the key to this. So thank you for your attention. I think we're going to take questions. Is that right?